Today we're going to be talking about continuity, and we're going to get another important definition. So I'm going to ask you which one of these two functions are continuous. A, if you're tracing the curve, you trace it along, trace it along, trace it along, not lifting up your pencil at all to get to any other points. But for B, tracing along, tracing along, tracing along, tracing along, to jump down here to get this value and then jump back up and trace along. So which one of those two functions are continuous? The answer is A, because B has this jump to it. So this definition, and I want you to know this definition, the function value exists. And then the limit also exists from the left and right. A lot of times you're going to have to be showing the limit from the left is equal to the limit from the right, and then the limit equals the function value. And there are a lot of different types of discontinuities, and I want to make sure you have these in your notes because this is actually something new the AP is testing us on. Is they're asking you guys what type of discontinuity we have. So A is continuous everywhere, but B and C are both removable discontinuities. I have just one point that I'm removing. Here, it doesn't even exist. Here, we have it moves up and is a different function value. When your function jumps to a different value, so that's something like when you're talking about absolute value graphs or piecewise functions. When you have a vertical asymptote, that's an infinite discontinuity. And then an oscillating function is when you oscillate, and if you look at this function, it's really hard for you guys to see that. But if you graph this function 1 over x in your calculator and you zoom in, as you get to 0, it's going to keep oscillating back and forth. So our limit here would not exist. Okay, identify points of discontinuity. State the type of discontinuity. Well, tangent can be written as the sine of x over the cosine of x. Whenever a fraction equals 0, that's when you have your vertical asymptotes. So that's at pi over 2 and 3 pi over 2. And then all rotations of that. Cosine repeats every 2 pi k. So you could write it like this, so that k is integers. Or remember, you know when tangent has vertical asymptotes. Tangent has vertical asymptotes at pi over 2 plus pi k, again, where k is integers. So either one of those answers would work. I thought of this one as I was making this video, and I realized that this was an inefficient way to write my answer. Our next one. Okay, we need to make sure, okay, so our function value exists. F of 2 in this case is 2. So that's the first thing we need to check. Next thing we need to check. Limit as x goes to 2 from numbers a little bit less. Numbers a little bit less, we're going to use 3 minus x. So this limit I can plug in 2 and get 1. And then the limit as x goes to 2 from numbers a little bit more is this function. When I plug in 2, I get 1. So our limit is equal to 1, but our function value is something different, so that is a removable discontinuity. And I just realized when I flipped over to this slide, I didn't give you guys the answer to the type of discontinuity for this problem, and that would have been an infinite discontinuity. I apologize about that. Okay, this is probably one of my favorite types of problems. Always shows up on quizzes and tests. Okay, lots going on here. Finding the limit. Limit as I go to 1. My left limit doesn't equal my right limit, so this does not exist. Limit as I go to 2. As I go to 2, left and right both equal 1. But my f of 1, f of 1 is equal to 1. Limit as I go to 4 from numbers a little bit less, that is also 1. And my f of 2 is equal to 2. Now, is our function continuous at 2? So I'm looking at parts B and E. Are those two things equal? No. And then give me a reason from that definition that I gave you guys for continuity. The limit as I go to 2 of my function value does not equal f of 2. Is a function continuous at 1? So I'm going to look at part A and C. Well, I can just tell you it doesn't exist. It's not continuous because the limit as I go to 1 of my function does not exist. Now the last one, are we continuous at 4? Now this is a little deceiving, and honestly, before I recorded this, I went to our book and I made sure I was correct on this. The limit exists and it equals the function value, even though there's nothing to the right side, because it's a one-sided limit and you have a function value. Yes, it is continuous. It's okay that it's just one-sided because we don't have anything on the other side of the graph. Okay, give a formula for the extended function that is continuous at a point. What they mean by that is you're going to write this as some piecewise function for all values except x not equaling 9 and x equaling 9. I noted that if I plug in 9, I get 0 on the top and 0 on the bottom. We have to do some manipulation. That manipulation, you could multiply the top and bottom by the conjugate of the bottom. But there's another manipulation I want you to be exposed to that I think is something of a fun manipulation. I leave the bottom alone. The top can be factored because this is technically a difference of two squares. Okay, this x is technically square root of x, square root of x. 9 is technically 3 times 3. Now I can cancel that out, so I have my function, hey, for f of x equals root x plus 3, for x is not equal to 9. And then what would that value be? What would fill in this hole? This was technically a hole here. So if I plug in 9 in for x, that would fill in the hole and get a y value of 6. Okay, find a value of a such that our function is continuous. So really we want the limit as x goes to 1 of numbers a little bit less. I'm choosing 1 because that's my breaking point in my piecewise function. Numbers a little bit less has to equal the limit as x goes to 1 from numbers a little bit more. Since these are both polynomials, I can plug in 1 for x. A is still my variable. What am I doing? I'm sorry, I have this answer wrong in my notes. 2 minus 4. If I subtract a 7 over, okay, so there our function is continuous. This shows up a lot on multiple choice questions, and I've seen it show up on some free response questions on our AP test. The intermediate value theorem. This is super, 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 super important, and I'm annoyed our book doesn't cover it as much as I want them to. Intermediate value theorem. This is super important. So basically the idea behind it, if I have a continuous function, so my function has to be continuous, on an x interval from a to b, then I have to have all of the y values from f of a to f of b. Or there guarantees there's some c in between a and b such that the f of c is between f of a and f of b. And we get into this a lot more. There's a lot more examples of this as we work through studying for the AP in March, but I want to make sure you guys know this now. Okay, so use our intermediate value theorem to show that this function has a 0 on the interval. Since our function is a polynomial, we are continuous, and I'll talk about how I want you to justify that in a minute. Find f of 2, which is equal to -4. Find f of 4, which is equal to 18. F of x is a polynomial and thus is continuous everywhere. You have to state that piece where it says we are continuous in order to use the intermediate value theorem. Since f of 2 is equal to -4 and f of 4 is equal to 18, there exists some value c such that f of c equals 0 by the intermediate value theorem. And you can use that abbreviation for intermediate value theorem. Okay, please for me make sure that you submit your lesson summary on time.